好，同学早哈。Alright, in Tuesday we have addressed the relationship of magnetic force, the Ampere force law, which addressed the relationship between currents and magnetic flux is produced. And if you move another section of current loop to the neighborhood of the source current, then it's supposed to experience the magnetic force as stated in equation 1.77. So because the formation of magnetic force is related to the cross product, that is, its direction is determined by the direction of flux density as well as the currents of your that absorb the force. So IDL specify the current loop, or at least the section of the current loop that you move into the neighborhood of magnetic field. Then using the cross products, right-hand cross product rule, you can determine the force experienced by the current section. And one thing to notice that is because equation 1.77 is determined in terms of the cross product. So the force direction is actually perpendicular to the current direction and the magnetic flux density direction. So it's orthogonal to DL and B as well. So that's of course, there are certain applications derived from magnetic force. Here's one important application, that is the speaker. Okay, even though that we have some other way to produce acoustic wave, this structure, the speaker, the configuration of the speaker is still the fundamental configuration that we use, that your Bluetooth earpiece has. They are still using the same structure. So let's check how these things works. So in this plot, you have a permanent magnet that has two polarity, the N-type polarity in the middle and S to the side. So the magnetic field is pointing from the center toward the to the outer wheel of the of this magnet. And in the middle is this is a cross-section view. So in the middle is the coil. So the loop, the wire loop. So the direction of the wire is winding down continuously into and out of the screen, and the coil is attached to a membranes, a membranes, to form the so-called speaker. So if the coil is moving back and forth, or to the left or to the right, as shown in this figure, the movement of the coil will perturb the position of the membranes, so that the membranes will be moved as well, so that, and according to the frequency of the movement, you can produce acoustic wave of different pitches, right? So let's see how it works. Supposing that the current direction is pointing outward on the top half and inward in the bottom half, then the current is flowing which way? It's flowing in this direction. So remember, using this relationship, the magnetic force experienced by this coil is IDL cross B. So at this position, the IDL is flowing this way, and the magnetic field is pointing upward. So the force shall pull the membranes to the left, all right? And on the bottom half, the current is pointing into the screen, and the magnetic field is pointing downward. So it also produces a force to the left. So the bottom half also pull the membranes to the left. So it's a consistent force to the left for the top and bottom half. If you reverse the current, so that on the top half is pointing into the screen and bottom half is pointing out of the screen, then the magnetic force experienced in this magnetic field will be pushing out to the right. So that will push the membranes to the right. So if you have an alternating current, AC current, then according to the frequency of the currents, the membranes will be pull and push and pull and push according to the frequency of the current signal. So the telephone, surprisingly, the telephone, the landline, 室内电话, the landline is pretty much the same about telephone had been invented about 150 years ago. So we still use this magnetic, of course, you know that the landline telephone has a speaker and a microphone. The microphone changes acoustic wave into electrical signal, voltage and current signal. And the voltage and current signal is sent directly without any modulation, which has been adopted in current modern communication skills. Modulation is a must, but surprisingly for landline, there's no modulation. The acoustic wave is transformed into electrical signal and sent directly to the other household. So as you can see in movies of several decades ago, for the World War II era, you need an operator to connect the lines from different households so that their telephone lines can be connected together. So at the other end, the current and the voltage and current, the electrical signal is transformed via using this speaker back to acoustic wave, so that you can hear what the people said from the other end, right? So you can try yourself with your right hand to see how this thing works. Well, okay, so it's very simple. So it may be to one surprise that at the age of great accident or great catastrophe, sometimes the low-end technology works best. For example, I remember about 2 or 3 years ago, there's a serious flood in China, and people from China always say that, we don't have to bring cash around. We can use our cell phone to pay our bill, to buy things from the convenience store. But when the neighbor is down, then, well, cash is still the best best medium for trading, right? So sometimes you need to have some plan B. Okay, the reason I want to mention that is at the time of earthquake or some great natural hazard, and well, at the beginning, the cell phone still works. However, if you are out of power for more than 12 or 24 hours, the UPS system in the base station will be depleted. Okay, but at that time, the landline still works. The landline still works. It can work without electricity. Okay, so it's quite amazing that the low-end technology can survive this kind of surprising event. All right, let's move on to our next topic. So we already introduced the formulation for magnetic flux density, which is written as B, so the magnetic flux density. And this equation 1.70a, has in fact a designated name, means Biot-Savart law. 有没有听过 Biot-Savart law? Right, okay, so Biot-Savart law helps you to determine the direction of magnetic flux density according to the relationship between the source current and the observation point. This figure is kind of interesting, all right? For the first few years of my teaching of electromagnetics, I saw this figure was drawn incorrectly, because when I use my right hand to find the direction of B, I always find that B should be pointing to the left of the plot. And after a few years of teaching, one day I finally realized that this drawing is correct. It's simply a matter of perspective. Well, I would like to comment that maybe the author, which as you can see from his name, is an Indian. He's from India. So, well, he probably used a different perspectives that we use too. Okay, so try this. So suppose you have a current source, IDL. So we only account a short length of it. And the direction in your observation point is P, which is a little bit off from the axis that align with IDL. Now that is a little bit off with the L direction. So the vector connecting IDL and P is AR. So you have a distance R, and the unit vector from DL to P is here, the AR. And using this equation, the Biot-Savart law, you should be able to find the magnetic flux density is pointing to this way. Can you do that? Do you believe that? Try, okay. Yeah, okay, all right. Well, okay, the key is here, okay. The IDL is coming from the back. It's not from the front, okay. So if you saw that this is from the front and pointing into this surface, then that should be to the left. However, it's coming from the back, okay, so it's pointing this way. This figure is fine, right? All right, so this equation is known as the Biot-Savart law, which is which can be an analogy of Coulomb's law, so that so its application is similar. So for very short pieces of current, which is dl, and the magnitude of the current is I, then the magnetic flux density is proportional to the inverse of the distance r, and is related to the material property mu sub 0. And because this is a very short current, short piece of current, so it can be regarded as a point source, similar to the Coulomb's law. So you have the 4 pi to address its relationship to the surrounding area. And the thing that is different from the Coulomb's law is the direction of B is determined jointly by the source position and the observation point, which is addressed by AR. So it's in the cross product relationship. So DL cross AR shall give you the direction of magnetic flux. And so next are some observations. The first observation is that the magnetic flux density is not distributed evenly in the space. Unlike Coulomb's law, which produces an electrical field that looks like a field distribution that is similar to a sphere, the distribution of magnetic force for a point source, for a short piece, is actually somewhat like a donut shape like this, because the current direction, if you are standing in front of the current line, then AR and DL will be of the same direction. Then the cross product of the two is 0. So magnetic field distribution is not spherical in the space. It's not homogeneous in the space. It actually looks like a donut. So it's the same on the side, and it's strongest on the side. And it becomes smaller and smaller when your observation is moving to the front or the back of the current source. All right, so as the figure suggests, it looks like a donut or what? Bagel, all right, okay, whatever. Yeah. So as you can see, because the cross product, which means it reaches a maximum when the difference between the two vectors is 90 degrees. So if you are looking from the side, cosine alpha, not cosine alpha, sine alpha equals to sine alpha equals to 1. Yeah, sine 90 degrees equals to 1. So you have strongest magnetic flux on the side, and it's 0 to the front and the back. So it's so this is the major difference toward electrical field produced by a point charge. Then nothing, okay. So the magnetic field or the magnetic flux are currents, looks like currents surrounding in the neighborhood of the current flow. So unlike the electrical field produced by a point charge, so you have a positive Q in the space, then your electrical field will extend to the infinity. If you have a short piece of current, then the magnetic field or magnetic flux produced in its neighborhood shall form loops. should form loops, so it has no ends. 所以磁场一定要绕回来成一个圈，它没有头没有尾，不像电场是可以有头有尾的有头有尾的。So that's another principal difference to the distribution of point charge. All right, so take a few looks at this slide and beware of the difference between magnetic field produced by currents and electrical field produced by charges. So go back to this figure. Let's do some simple calculation. Let's consider an infinitesimal length of 10 to the minus 3 meter of wire. So it's a 1 millimeter long current placed at a position of 100. 宣导一下那个助教改作业的时候说，很多人把向量还是写成100这样子我第一天上课的时候就跟你讲过，你向量请把它写成 ax 加 0ay 加 0az 不要写100然后我说那个写错了就扣2分吧满分10分我就写错扣2分不过我们助教人虽然看起来有点凶不过他还是蛮善良的，他说他只扣了0.5分OK， 所以以后请尽量那个基本上我已经讲过很多次了说考试的时候看到你还这样写的话，我可能心情会比较不好OK 心情不好你就知道下手会比较重OK。当然不喜欢太重手了OK 不要逼我就是了 OK 好，宣导一下了这个尽量写完整的那个向量表示示 OK。Alright, so go back to the problem so the source position is 100 and the amount of current is 2 amp and the observation point is actually 022. Okay. So one thing I forgot to mention is that the current direction is pointing to the positive x direction. So it's dressed as AX. And so how to deal with this problem? So first write up the IDL, which is 2 amp times 10 to the minus 3, which is the length of the currents. And here AX specifies the direction of the current. Next, we write up the vector between the source and the observation point, which is from 100 to 200, about 022, so which is, it becomes minus AX plus 2AY plus 2AZ. So that's the R vector. And substitute all the information into the Biot-Savart law. You can calculate the magnetic flux observed at 022 as this, which is in the direction of minus AY plus AZ, and the magnitude is can be represented with this number. Okay, so you should practice this example. So the Biot-Savart law can be used to find magnetic flux density due to a current carrying filamentary wire. What is filamentary wire? 就是很细很薄的一条线啦OK, of any length, 也就是没有厚度啦也是没有厚度。Of any length and shape by dividing the wire into a number of infinitesimal elements and using the superposition. So similar to what we have done in section 1.5, the calculation of the total electrical field of sophisticated geometry can be dealt with using the divide and conquer strategy, that is, divide complicated current distribution into small pieces of current lines, then apply the Biot-Savart law to calculate the total magnetic flux and using the superposition law. So Next will be some example for demonstration of this idea. So example 1.11, considering that there is an infinitely long current line. So unlike example 1.6, which is an infinitely long charge line, this is actually a current line. Okay, so on this infinitely long line, it has a homogeneous static current of I. And as you can see from this figure, the line source is placed in parallel with the z-axis, so flowing upward as the figure shown. So as you can see here, we should adapt the cylindrical coordinate system to better address this problem. It can be the cylindrical coordinate system is actually more suitable for line source. All right, so the current is placed along the z-axis, and the observation point can be anywhere in the space, say this point, which is addressed as r, phi, 0. R is the distance to the z-axis, phi is the angle with respect to the positive x-axis. Z is the height. And because this line is infinitely long, so you can offset the height to 0 to simplify the problem a little bit. Okay, because the line is infinitely long, so any place can be defined as the origin, or z equals to 0, so that the computation can be somewhat simplified. Well, actually the answer is labeled to the right, okay, but let's go through the process. So, as I mentioned in the previous slide, it's more convenient to use cylindrical coordinate system for line source. And we try, of course, we need to adopt the Biot-Savart law, okay? So, according to the Biot-Savart law, here is our constant. Without any further specification, we assume the environment is a vacuum. So the permeability of vacuum is mu sub 0 divided by 4 pi. And the current, which is IDL, is replaced with I dZAZ, because we know that the infinite line source is placed along the z direction. And AR is the line between the source and the observation point. And R to the square is the square of the distance among the two. And next is to interpret the cross product. So according to the figure, and use your right hand, you know that by taking the cross product of AZ and AR, what is the result? It's a new vector lying on the z equals to 0 plane, which can be addressed as the horizontal plane or the xy plane, because of the cross product relationship, right? Do you get it? 试着用手比看看了哈，你那个 AZ cross AR 之后的那个向量是其实落在 XY 平面上面的，也就是这边画的 A5 方向上所以相对变得简单So the new vector of the cross product is in the A5 direction, and the magnitude will be psi alpha. Because the two AZ and AR are both univectors, so the magnitude of the cross product is 1 times psi alpha, which is the angle labeled in the figure. All right, so the problem becomes, what is sine alpha? Well, sine alpha is actually lowercase r over capital R. Okay? Using these two relationship. Okay, in the denominator is the capital R, which is the distance between source and the observation point. And in the numerator is lowercase r, which is the distance from the observation point to the z-axis. So you can substitute sine alpha with lowercase r over capital R. Then the magnetic flux density can be rewritten as lowercase r over capital R to the cube. And finally, we can substitute the representation of capital R, which is the square root of z to the square plus r to the square, and get the representation for the magnetic flux produced by a short section, but produced by a short current section. And of course, this is not the end product, final product of this example. What do you need to do? Well, you need to do the line integral over the total length of this infinitely long line. Then we may need some tricky part over here, right? 不好意思，要开外挂了哈。Well, so the total magnetic flux at the observation point are phi 0 due to the presence of this infinitely long current line is the integral of the B from z equals to minus infinity to infinity. So substitute what we have in the previous slide over here. And we need to do the what? Okay, the integral over z. And it seems a little bit difficult to carry out this integration. So the trick is use change of variable as shown in the top right figure in the red box. So by changing the, similar to the example that we use we see in example 1.6 or 1.7, similar approach. You can replace the integrand from z to alpha, which means the integral limit is changing from minus infinity to infinity to minus pi over 2 to positive pi over 2. So by doing this, well, you can recognize 不好意思，我讲错了哈。这个积分其实没那么难哈，只要你知道答案的话。Okay, suppose actually the integral of this thing is not that difficult. Okay, it's actually the differentiated result of this expression. Okay, so suppose you are really good at this, you can carry out the integration from using this relationship and get the integral of this thing is actually 2. So the result is becomes mu sub 0 times I over 2 pi r a phi. So the reason why I place this in here is to make a comparison to address the relationship of an infinitely line source of charge and infinitely line source of current, and see the energy between electrical field and magnetic field due to similar source distribution. So in the result, we see that from an infinitely long current line, the magnetic flux produced is mu sub 0 I over 2 pi r, and the direction is a phi. So what the result suggests? It suggests the magnetic flux density is proportional to the magnitude of current. Well, that's trivial. Okay, the stronger the currents, the greater the magnetic field is. And B is inversely proportional to R. So we have seen this. We have seen this in Biot-Savart law for a point charge. The magnetic field is inversely proportional to the square of the distance. In Coulomb's law, the electrical field is inversely proportional to the square of distance. However, if you upgrade your source from a point source to a very, very long line source, then the total influence of the line source is, of course, stronger. So you see the electrical field due to a electrical line charge line source is inversely proportional to R. And for an infinitely long line current, the magnetic field is, again, inversely proportional to the distance of R. Okay? And the 2 pi suggests that this field is distributed evenly in a cylindrical fashion, right? So in the formulation of B, you see the influence of geometry, R. You see the influence of the source intensity, I. You see the influence of the material of surrounding area, mu sub 0. Okay? And another important difference between B and E is B is directed in a direction that is orthogonal to the line source direction and the direction that are joining the source and the observation point, while for electrical field, the electrical field direction is simply placed on the line aligning the source and in the observation point. All right? Okay, so the calculation of magnetic flux density due to the presence of current source is still valid for calculation of line source, surface current, surface current, line current, surface current, and bottom current. Okay? So line current is simply to imagine, as supposing that you have an electrical conducting wire. Of course, you have a line current. So what is surface current? Well, if your conductors is if your conductor is a planar conducting surface, of course you have surface current. How about bottom current? Can you imagine can you have any example for bottom current? 空间里头分布的空间分布的电流形式有没有？有，头上有一个 ，OK 好。但你我头上的是，你头上的不是哈。你头上看到的日光灯管不是真的日光灯管，不是20年前的日光灯管，你头上看到的是用那个 LED 假装的日光灯管，OK。但我头上的这一个你只要跑过来我这边看的话是了它是真的日光灯管，OK。那日光灯管它其实里头是什么电？它其实是低温的普拉斯玛 低温的电浆就是两边通电，让里头的那个气体产生导电，那个导电的过程当中，它的那个能态分子的那个分子的能态会上上下飘了然后当它掉下来的时候，那个能量差就发光跑出来了所以日光灯管的那个日光灯其实是一个低温的电浆体所以里头通的那个电浆其实就是一个 violent current so this is one example of violent current. Alright, so violent current is addressed as J, surface current is addressed as JS, and line current, well, line current, do we have any? Okay. The current density are vectors since the flow is involved. The flowing direction is involved. So you can see here J is written in both phase. So they are vectors. So this is the surface current density. J is current density. I is current. J is current density. So you have line current density, surface current density, and volume current density. All right. And the volume current density of uniform density flowing in a straight wire, as shown here, can be found by as the total current, the total currents of a uniform current density can be found by taking the product of J and cross-section area A. So I equals to J times A. If the current is non-uniform, then the total current I should be found out in terms of integration. So the total current can be found by taking integration of current density. So next, in example 1.12, we shall calculate the magnetic flux density due to an infinitely large surface current. So before we proceed for the solution of this example, let's try to guess the result. So if you have a point current source, the magnetic field produced by the point current source is inversely proportional to the square of distance. If you have an infinitely large source, the magnitude of magnetic fields is inversely proportional to the distance r. How about if you have an infinitely large surface current? What is the relationship between observation distance to the magnetic flux density B? Let's guess. What's your guess? Well, similar to the electrical field distribution of charge sources, we should guess that it's not related to the distance, the observation distance. The magnetic flux or the magnetic field intensity produced by infinitely large surface currents should be the same everywhere, should be homogeneous, everywhere. Even though that in reality we do not have infinitely large current surface. But anyway, let's try solve this problem. So again, using the divide and conquer strategy, we can divide a surface current into an assembly of line currents. So as this figure suggests, a very large surface current can be divided into many pair of line source. Here's one, here's another one. Why do we use two lines together? Again, because symmetry in the geometry, okay? So in the previous example, we know that the magnetic flux produced by an infinitely long line is 2 pi, is mu sub 0 over 2 pi r times I. And the direction can be guessed or can be predicted by right-hand screw. So the magnetic field produced by this line is pointing which way? It's pointing this way. So it's labeled as dB1. The magnetic flux density produced by this current source is this one, dB2. They are all placed on the xy plane, that is the z equals to 0 plane, this horizontal plane. dB1 and dB2 can be decomposed into two directions. They have projection along the y-axis, and they also have projection along the minus x-axis. And note that because of the two pairs are placed, the pairs of currents are placed in symmetry toward the z-axis. So the projection of dB1 on y-axis, it happens to be of the opposite direction of the projection of dB2 on the y-axis. They are of the same magnitude due to the geometric relationship, and they are of opposite direction. So their projection on the y direction cancels. Nevertheless, their projection along the minus x direction adds up. Okay, so it becomes 2 for their x direction projection, all right? So the projection can be found as cosine alpha. And according to this relationship, cosine alpha can be written as y over square root of x to the square plus y to the square. Okay. So we only have the sum of dB1 and dB2 is dB, which is pointing along the minus x direction. And they are added up. They can be found as dB1 times cosine alpha times 2, because the projection along the axis are the same for dB1 and dB2. Okay, so minus ax suggests that this new vector is pointing to the minus ax direction. And cosine alpha can be found here. And the rest can be found using the line source magnetic flux density equation, like this. Okay, so you substitute all the geometric parameter and the current density into, that is, I, the total current, which is thin strip surface area, can be found as dx, that is the width of the current, times the surface current density, Js0. Js0 times dx times mu sub 0 divided by 2 pi r. Okay, so for the pair of current source, the magnetic flux due to the pair of current source is this. To find out the final solution, you need to do what? Well, we need to do integration along the x direction. And because you already divide the surface current into pair wires along the x-axis, so the integral becomes dx. And the limit is from x equals to 0 to x equal infinity. So suppose substitute everything in here and identify that y over x squared plus y squared can be substituted using change of variable. 外挂式子放在这里了哈 ，OK， 有没有看清楚啊？下面这个是 a， 也就是说这边的 x 平方加 y 平方可以看作是 a 平方加上 x 平方哈。那 x 是这边的积分的那个单元，要积分的那个要被积分的东西嘛哈，所以在这边。So identify the using this relationship, you can replace the x as arctangent of x over a, so that you can replace the variable, replace the integrand from x to angle, and the limit of this alpha of this angle is from 0 to pi over 2. So the limit was changed. Well, 0 and pi over 2 is the result of arctangent of x over y by replacing x with 0 and infinity. But anyway, after the replace of after the change of variable, this integration becomes relatively simple to carry out. So it simply is 2 pi over 2 minus 0. So the end result is here. The total magnetic flux density is minus B sub 0 J sub S0 divided by 2, and the direction is AX. Well, in fact, the direction is minus AX. For observation point with y greater than 0. On the other hand, if observation is placed on the other side, which is y is smaller than 0, then the direction of magnetic flux density is pointing to the opposite direction, which is positive x in this case. And take a second look at this result. It confirms our prediction that if you have infinitely large surface current, then the magnetic flux density is not related to the distance of observation points. As you can see here, there's no R plays no role in this result. It's a constant for any place or any observation point. The magnetic flux density is related to the material property, is proportional to the strength of the surface current, and is not related to the observation distance. Okay, so if you draw this result graphically, you can see that the dot represents surface currents going outward. So suppose you have current world along in this way, then the magnetic field, which can be guessed largely by the right-hand rule, is pointing to the left on this side and pointing to the right in this side. Okay, so you have this result for your magnetic flux density vector. All right, so here is the more general way to write up the magnetic flux due to the presence of infinitely large surface currents. So to put it in a more general way, we replace AY as AN, the normal direction of the surface currents. Then the total magnetic flux can be found out using this relationship, that is JS cross AN shall give you the representation of your magnetic flux density. All right, so let's break for 5 minutes.